So in the Nash game, all the players make their decision simultaneously. So in a continuous time setting, when we mean simultaneous, it is, so in a discrete time setting, simultaneous means they make the decision every period. But when we say they don't make it simultaneously, it means that one person makes it before the other person. Okay? Well, in continuous time, it is very difficult to know what is before and what is after, right? So we write, for example, notation like t minus just before t, we write t plus just after t, but they are only in the limit sense. They're actually happening simultaneously in terms of temporal setting, but the reason we are saying not simultaneous is because there's a hierarchy. That means there is a dependence of the decision of the one person on another decision. So in that sense, there's a hierarchy. The way to formalize them would be divide the period in small deltas, like delta 2, delta 3, delta 4, delta. And then one person makes a decision, the other person follows with a decision in the next delta period. And then the first person makes a decision again, the next person follows the next delta period, and then delta go to 0. So that's one way to formalize a hierarchical setting of decisions. So in the Steckelberg, feedback Steckelberg, we're now saying that there are two players who make their decision in a hierarchical manner. That means the player having the right to move first is called the leader, and the other player is called the follower. So if there are two or more leaders, then the leaders play Nash. If there are two or more followers, then the follower play Nash. Nash means they followers all decide simultaneously, leader all decide simultaneously. But let's limit ourselves to one leader, one follower for the time being. And one leader, one follower, the issue is clear. And we also call these games leader-follower games. But the reason we call them Steckelberg game is because von Steckelberg wrote a book in 1930s, and he proposed these games in a single period setting, in a static setting. And since then, they've been generalized to multiple period settings and also to the continuous time setting. So what we are now doing is the Steckelberg games in continuous time. So they're called Steckelberg differential games. And once again, we can have an open loop and feedback solutions. So in open loop, what happens is that the leader decides the entire strategy of the time horizon at time 0. And then the follower decides his strategy after knowing the leader's strategy. It is clear that in general, the solution will not be time consistent. By that, what I mean is that if you have a solution as a function from 0 to capital T, let's say, and the other person depends and makes his decision based on the decision of the first person, then let's say after one period or after a certain time has passed, at some t, which is bigger than 0, if you play the game again, then the solution that you obtain may not be the same as what we did before. Because remember, if you let's say t equal to capital T equal to 5, and we have a decision for the entire 5 periods. This is continuous time. And now after 1 period, we play the game again, then our decision will be only 4 period. We will come with a new set of decisions. That new set of decision may not be the same decision that is the 4 period part of the 5 period decision, right? So that means that I can change. So if the leader feels that he has an advantage of changing his decision, then he will do so. He has an incentive to do so. He may not do it, but he have incentive to do so. And the only way to say you can't do it is to have a credibility or some law by which he's not allowed to do so. But anyway, we're going to do, and when it comes to open loop, there are a lot of papers on open loop Steckelberg games, but I think that that is not what we should be looking for. And so I do feedback. We also have a paper in 2-period games in inventory models, and that was written by the people, one of my doctoral student here, Tao Li, who is now tenured professor at UC Santa Clara, and a postdoc. And we show that if you have a 2-period problem, a supply chain of 2 periods, supply chain, single period supply chain in our literature is a Steckelberg game, because in a single period there's a manufacturer and there is a supplier and there is a retailer. The supplier makes a decision about the wholesale price. It's a news vendor problem. News vendor problem is a Steckelberg problem. It's a single period Steckelberg game. And the entire coordination, supply chain coordination literature in our field, if you know what I'm talking about, is all single period. And so Tao Li and I wrote the first paper on 2-period Steckelberg game supply chain and created a coordinating contract for 2 periods. And we are working on a paper. I think Tao is a little bit lazy. We are working on a paper called 5 Steps to Supply Chain Coordination, which should have been finished 3 years ago, but is not. And hopefully we'll finish it this year. And that is because I've been working on dynamic Steckelberg games, which means that if you want a dynamic supply chain, then you need dynamic Steckelberg games. And our operations research literature is not very comfortable with this, because they really are not into this kind of methodology is not part of our operations research. So they go into single period and then leave. And now they do something else. Again, single period asymmetric information, then they will probably leave and then do something else. At our school, it's probably one of the leading school in dynamic games in business schools. And Ben Susan and I usually work in this area, and we have applied this to inventory problems, but this is continuous time. We haven't done any inventory. This is an advertising kind of game. Okay. So if you want time consistency, you want feedback, and that's what we do. So let's see what is going on here. A little bit of a literature here. These guys, this is a classic book now, Bassar and Osder. They wrote a book called Non-Cooperative Games, and they do a Steckelberg discrete time. They also do continuous time, but the continuous time, they don't develop the entire theory. And the entire theory for continuous time is actually being developed in this paper by Ben Susan and Chen and Sethi in 2019. Or maybe this is another paper where we develop, no, actually it's a more recent paper, it's one with the Hong Kong authors. And that's where we develop the theory of this these games a little bit more detailed than Bassar and Olst. But Bassar is a famous guy in game theory. He's also a big professor at Urbana-Champaign. He's also one of my co-authors. Ulster is a famous guy in Amsterdam, and he has been in game theory. He's been in game theory for a long, long time. And for those who don't know, it is one of his papers that he published many, many, many years ago that actually became the source of justification of China's single child policy. So if you search internet, single child policy, mathematical foundation, you will see the Ulster's paper. Okay, so just remember this. This guy said that he would have never written a paper if he knew that this is going to be a basis of the policy, which he does not approve of. Okay, with that little part, we're now going to go to Hay, Prasad, and Sethi paper of 2009, which is where we do the Steckelberg game for this problem called cooperative advertising. So what is cooperative advertising? The cooperative advertising is an idea by which the manufacturer provides retailer the support for retailers' advertising. The idea is that retailers are close to the market, so they know what and where to advertise. But if they don't advertise enough, then they lose the sale and the manufacturer lose the sale. So the question is it possible for the manufacturer to say to the retailer, hey, I will pay part of your advertising. So if you pay $100, I will pay 10% of that. So 10% is the subsidy. Or if you use this amount, I will pay 50% of it. So the 50% is subsidy. And clearly you can solve the problem with zero subsidy, but we can show that zero subsidy is not optimal. We can show that optimal solution may require some subsidy. Now, this is what we can show, and other people have shown in a single period setting. But the cooperative advertising has been in practice for quite some time. So this is more a theoretical foundation of the cooperative advertising, okay, in some sense. The amount of money that goes into cooperative advertising in billions of dollars could be $30-40 billion as of now. So it is a huge amount of money that is being given in cooperative advertising by manufacturers to retailers. If you read those papers, you will probably see the empirical papers where they tell you the amount of money that is being used and the amount of subsidy. Subsidies could go as high as 80%, 70%, 50%, and all of that, even 100% in some cases. But anyway, so we're going to define a subsidy rate WT, which is between 0 and 1. And now you know why I want to change the W in the previous slide to be something different. It's not confusing because this is a process that's a constant. So it's not confusing, but I'm just going to do it anyway. Okay, so we have a control variable called subsidy rate, and we have effort level by retailer, which is advertising effort. This is the decision by the manufacturer. This is decision by the retailer. And the idea of Steckelberg is that the manufacturer first says, I'm going to give you this much subsidy. And then the retailer says, okay, if you're going to give me this much subsidy, this is how much I'm going to advertise. So there's a reaction function. You give me this subsidy, I'll advertise this much. Think about single period now. If you give this subsidy, I do this much. And then there's an equilibrium. In equilibrium, there's a subsidy level and there's an advertising level, which is an equilibrium. Okay, an equilibrium in a similar sense in terms of the inequalities. There will be two inequalities, just like in Nash, but there will be slightly different nature of inequalities, and we talk about that, I think, in this chapter, but we also talk about in this paper. Although in this paper the description of the hierarchy is not completely correct, but we did not try to fix it because we wrote other papers where we corrected that. So in Ben Susan et al., we have a correct formulation. There are other survey papers that I've written which we have fixed that problem. And so if you read that paper, the description of the hierarchy is not completely correct. Although it'll be difficult to find out what is not correct, but it is not. Okay. So first, let's formulate what's going on. This is our dynamics. This is straightforward single-person Sethi model. But the objective function now is different because the dynamics is faced by both the manufacturer and the retailer. But the cost of advertising effort, which is UT square, UT is the effort, the cost is UT square, part of the cost is paid by the manufacturer. So you see the retailer's cost function, he makes this much revenue, but his cost of advertising is only 1 minus WT times this, because WT part is paid by the manufacturer. That part is paid by the manufacturer. So his cost is this much. So that's the retailer's objective function. But the manufacturer's objective function also is different because he pays this cost of that advertising. And he has his own revenue, okay, which comes out of wholesale price because he's selling it to the retailer and this guy is selling it to the market. So there are two different margins and there are two different costs, but the cost of advertising is split this way. And so they go into the objective function appropriately. Any questions so far? So the solution really depends on the available information structure. We know that everybody observes the state, which is the market share. It's a full observation, although I recently saw a paper on Steckelberg differential games. Was it Steckelberg? Maybe Nash, where you have asymmetric information in continuous time. Not many papers like that, but I just recently ran across it. I sent it to Ben Susan to see what's going on there. Okay, so we have each time the player knows the current system state and the follower knows the action of the leader. At any time t, I know the state, I observe the state, and the retailer and the follower in general setting knows what the leader decided. Okay. Or other information structures, different definitions of equilibrium concept. You see this paper. This is the SIAM control paper in 2015. This was Shaquan Chen, who was a student here, and he's now working for Target. And his wife was a PhD student in Minnesota, I think, and she's now working as a professor at Temple University. So here's a rule that define the sequence of actions. So this is a correct description. So don't follow the description of Prasad or Hey Prasad and Sethi. The model is correct. The description is being fixed here. And the fixing takes some time. So that wasn't done in that paper. And if you did it this way, who knows? The referee would not understand it too in some cases. So the manufacturer observed the market share XT at time t. And after he observes the market share, he selects the subsidy rate, WT. Then retailer observes this section. And then he selects U sub t as a response to WT. Now let's see what's going on here. Here's what's going on here. This guy, manufacturer, decides WT after observing XT. So his WT is a function of XT. It's a feedback on XT. Now, if you do any single period feedback, it goes like this. News vendor problem. The manufacturer decides the wholesale price. Retailer reacts to the wholesale price and decides how much to order. But both people know how to solve mathematics. So the manufacturer knows what the reaction function of the retailer is. Okay? So manufacturer incorporates the retailer's reaction function into his decision of the wholesale price. Then with that reaction function, optimal reaction function for any wholesale price, he decides the wholesale price, optimal wholesale price for him. Once he decides the optimal wholesale price, the retailer's decision is already decided because the retailer is the response to the wholesale price. The entire response is known to us. So the response to the optimal wholesale price is also known to us. So the optimal wholesale price and the optimal response to the optimal wholesale price is the Steckelberg solution. That is how we do that. Look what's going on here. This guy has a function of XT. The retailer only reacts to the dollar value of WT, percentage, not the function. His UT, advertising rate, is not a function of W of X. It's not a function of a function. Now, if you say both are mathematicians, then of course retailer knows the function. But he's not going to react to the function, and that is important. And if you write all of that, you lose some referees sometimes because they don't know what's going on. So there is a certain discipline here that has to be understood clearly, that the retailer cannot observe, even though he knows, he only reacts to the current WT. And if he reacts to the entire function, then the problem is very difficult to solve. And it's not time consistent either. That's closed loop, by the way. So we are doing feedback, not closed loop. And we are not doing open loop. Okay, so I already mentioned that you can think about this as a sequence of small time periods and then take the limit. That is what Basar also do, but we don't do it that way. We, in our paper, in 2019 paper, we have a different formalism. We're going to talk about this soon. So we now decide how the players behave. So the way the player behave is that they solve this mathematical problem, and that gives them a menu called W of X. It's a function feedback, optimal feedback on X. It's a menu. That means it's a table. So every time T, the leader or the manufacturer observes X, which is the market share. The retailer's market share of the whole market. Remember, there's no competition here. The market share means total share of the total market captured. Knowing that, he decides W. So it's a table. Give me X, I give you W. That's all it does, right? Follower has another menu. His menu is a function of X and a function of W, not a function of W of X, not a function of the function for each X. It is, you could call it a W of X for that X. Yes, you can do that. But it's not W dot. The function will be W of dot, means for every X. So he observes what this guy tells at time T. So he says, okay, I'm going to give you 10%. He puts that 0.10 here. And he has his own table. He observes the X, he observes this guy W, and then he puts that into his table and gives you u. That is the way this has to be interpreted. You cannot write u of x w dot, even though the guy knows w dot, because he can solve the mathematics problem just like the manufacturer can. Everybody can solve. But then that game is not solvable by both. That game is too complicated to solve, and it's not time consistent, and we don't want to solve it. And we also show that this game is enough for us to coordinate the supply chain, so there's no reason to go any further. So I argue in my paper that feedback is the right concept here. No need to go more complicated. Because if I coordinate, I can do the best anyway. Okay. So now we define a feedback stakeholder, and we define the following way. And we didn't do that in the Prasad-Sethi paper, because we wanted to. Well, first of all, we wanted to limit it to Palm's audience, so we didn't want to get into some of these concepts. Secondly, that we were not completely. We knew what's going on, but were not able to explain it completely the way it should have been explained. So let's put it this way. We didn't realize that we were writing something that was not correct. Okay, so script W is all functions of W that takes X, which is between 0 and 1, and gives you a subsidy rate between 0 and 1. So it's a function of this domain to this range, okay? And we assume that this function is Lifshitz continuous, because we need Lifshitz continuity in terms of getting a solution of the differential equation. We have u, which is a script u, which is to take the function from x and w into advertising effort, which is from 0 to infinity, which is bigger than or equal to 0. So this is a function like this. So you can see we're limiting ourselves to these to be the sets of functions that we are interested. Now we define a Steckelberg game. For a pair of strategies WU, which that should be an element of WU. For a pair of strategies WU, an element of WU, yeah, I don't know why this subset came in here. Let YS, so I am at now T. Because remember, it's going to be a time consistent, so I have to go at any T, and it applies to any T. So at any T, I am given a value X of the market share. And I want YS to be the solution of the equation given W and U, or given U in this case, because W doesn't enter, but given U, W and U. I want this to be a solution of the differential equation going from T to some value S. So for every S going to T, I write the equation YS, which is U, YS, WS, 1 minus YS. Okay, so given W and U, I have a WS, because given W and U, it's a function. So I have WS and YS. And so I have an equation. You should note that the YS here stands for YS at T at X given W and U. So given W and U, this equation has a solution written this way. Kushali, make note that 48 needs a little correction here.
Okay, what is the correction again?
That subset should be epsilon, not epsilon, but belongs to.
Belongs to, okay.
I will look at it also, what is happening in the book later. Let me see what's going on here. Okay, so we have a solution. And now we have a solution. Now we have a solution. We know ys at every time s. We know what is w and u. Now we can define the objective function. So given w strategy, now see I put a dot here. So given the strategy, and given that strategy, okay, I now have a definition jm and a jr. We can define those. Define that from t, because we are now at t, all the way to infinity. We define that. I take the discount rate that goes from any t to this s, so I have this rho s minus t. Then market share is ys at time s, so pi m times ys. Then my cost, this is the manufacturer, so my cost is w of ys, because I was doing feedback on this ys, so w of ys, and I'm multiplying on u. U is behaving on ys and a w of ys. So when ys is known, we know u. U is a function of w ys and w of ys, or that ys. Not like this, not like this, it's this. So that is his. And this guy's objective function can also be defined. Similarly, it's now 1 minus w here. Okay, this is pi instead of pi m. Where we should stress the w and u, this evaluated at any state c are this and this. That's the definition of this function if you evaluate it at that point c. Okay? Now, a pair of strategies, w star. See this, Kusali? See that symbol? That symbol is what's going to go there. Oh, what's going on here?
Yes, so it's the belongs to, right?
Yeah.
Instead of the subset.
So a pair of w star u star in this set is called the feedback cycle equilibrium if Jm at w star u star of w star. Remember, this is the integral. This whole thing is the integral, so we need to know entire trajectory for us to be defining this. Is bigger than if w decided to change its policy w star to w. So if you take any w in script w, take x, any x between this, then any w and any x, then this quantity is not as good as that quantity. Remember, u star, the response is not changing. So in a Nash, what the other guy doesn't change is his action. In feedback Stackelberg, what the other guy doesn't change is not his action, but his response. So we are now saying that given that the response of the retailer stays at u star, if I change w as a manufacturer, I will lose. Remember, this is evaluated at this w, not at w star. And this w is this integral. Remember, this is well defined now. This function is well defined for every w and every u. So I can define this way. Sorry. Why is that? Why is not that going? Well. Yeah. So I can define that at w star and u star and w star, and I can define at w and u star. So w and u star, you can see this thing. I changed the w star to w, and I have a definition from the previous slide, definition of this and definition of this. So I can do the inequality, and I can say that for every w and for every x, this guy is worse off if he changes w star. Let's look at the retailer. The retailer doesn't change his action. Action is subsidy rate. Retailer changes. No, action is advertising. The retailer is advertising. Instead, he changes his response because that's what Stackelberg game is. So if return, so this is the equilibrium. Again, the left hand side is the equilibrium. Right hand side says that if this guy keeps W star, doesn't change his action subsidy rate, but that guy changes his response function from U star to U. Remember, U is operating at W star because W star is not changing. So for any U, script U and any X, this function is better than this function. You can see we can define the Stackelberg very similar to Nash. But what we have to do is who's changing what. The space of changes to define the equilibrium is different in Stackelberg than in Nash. But the inequalities are similar. It's if I change this script U to another, just the space of U, then it becomes Nash. The definition basically changes how I define, sorry, something is going on. Something is not doing good here. Yeah, so the definition changes how I define U script. See, W is defined as a W. If I define U just like that one, U 0, 1 to infinity, and not like this, then that definition becomes Nash. So the entire game of defining Stackelberg differential game equilibrium is defining that script U. Once I define that, inequalities automatically take care of themselves. If I define it Nash way, it's a Nash game. If I define Stackelberg, you see it's a function of X and W. That's not the case in Nash. I cannot have this in a Nash. If I remove this W here, then the definition becomes Nash. So that's what's going on. So that's a handful of things to write, and we did not write in the palm paper. But now it's clear. So we have defined what a Stackelberg equilibrium is, and now the mathematics of the control theory comes in. We show in this paper that if I do all of this I just told you and find a pair of Hamilton-Jacobi-Bellman equation, and where the game is played at the Hamiltonian level, then I have an equilibrium. It's called verification theorem. That verification theorem was not available in the literature, although people thought when we sent this paper to Math of OR, they rejected it. They said the mathematics is too simple. Our argument was the simple is good. That is not appear in the literature. This is the first time we have given a verification theorem. We have defined a sufficiency condition of an equilibrium. If it's a simple proof, so much the better. Now, so we finally sent it to Siam Control, which is by far a better journal than Math of OR. So our argument, our conclusion is that Math of OR referees did not understand the idea. Okay, so here's the Hamiltonian of manufacturer. Is defined in terms of lambda m. It's defined in a regular way of integrand plus lambda m times the dynamics. And so we have the Hamiltonian. And the game is played at each time at the Hamiltonian level. We're now playing a Stackelberg game at Hamiltonian level each time. Okay? So we do Stackelberg game. The first order condition for maximizing. Now, first we should maximize this. So let's see, I changed 2. So first the retailer. So what a retailer does. Oh, I'm having a problem with this. Okay, I'm having a problem here. Okay, so the retailer is going to take the derivative with respect to this quantity here and define u. Okay, so take the derivative and we get u star x w in terms of lambda and w. Okay, that's our function u star x w. That's a first order condition. And we can put the optimal response of this into the Hamiltonian to obtain the Hamiltonian with the U star. So now this becomes just a function of W and X. Okay, so we have a Hamiltonian now defined this way. And then we go to define, take the first order condition of maximizing this HM. So what we are now trying to do is took the response function of the retailer into account to formulate our Hamiltonian, that's a manufacturer's Hamiltonian. Then we try to decide what is the W. So we now can take the derivative of this with respect to W. That's a single period game that's defined in our supply chain literature. That's like news vendor. Every period we are solving a problem like news vendor in some sense. So now we get the first order condition Wx in terms of this. Remember, W can be only between 0 and 1. So we have to take the Wx. Wx bigger than 1 makes no sense. Because I support you more than one, then the retailer is going to use infinite advertising. If I give you more than 100%, even 100%, there's no reason for retailer to cut on advertising because everything is coming from the manufacturer. So there is no way the mathematics will give you more than 1. So one side is clear, but it can go below 0. That's possible. So we have to say max 0 and this. So if this becomes negative, we have to set 0. Okay, this is important. This is all in the paper. But these are important issues to deal with, and that's what's happening here. And then we substitute. We have 2 cases now because we have this function is like this, so we can substitute this. But we substitute this, we're not going to be able to solve anything. We need to solve. We have to identify where this happens, that happens, and we can do that. We can identify both of these and then solve the problem. And we did solve the problem in the paper, and it's here too. So what we do now is, first of all, remember, we have lambda m and lambda r, and they are Vm sub x and Vr sub x. By the way, when I'm looking, I'm looking at your pictures. So I don't know how it shows up in the video, but I'm looking at your picture to talk to you in some sense, and I'm looking at down below where I'm speaking. So I substitute Vm sub x and Vr sub x. And when I do that, I get partial differential equations. So I have this, well, because there's no t. So basically these are second order differential equations, but they are coupled. 2 value functions coupled this way. And if I can solve them, I get those value functions. And if I can solve them, I get the value function. Then I can get the derivative of the value function, so I can find out W star x. I can find out when it's 0, when it's not, because if it's negative, I set 0. And I can also find I can also find this. So where are we now? Let me see. Yeah. So once we have that, we can find both W star and U star. And then when there are 2 cases here, and we determine the condition required for no subsidy, which means this 0 to be optimal. We actually a priori can tell you which is the case. And then we can solve those 2 problems in 2 different cases. So first case is now cooperative advertising, which means W star is 0. And if we insert that, we get these equations. Okay. And we solve these equations. And we solve these equations by a linear value function. And we find that this is a quadratic equation, and then all of that can be solved. Okay, these are algebraic equations, and we can solve basically explicitly these equations. That is simpler case. The other case is more complicated. Let's see what's going on here. Yeah. So using, okay, so here's what's going on here. Using this thing, we can write U star, W star, and we know that the condition for W star equal to 0 is this condition. This condition comes from the fact that it comes from here. If this guy is less than this guy, then this quantity will be negative, because all of these are positive. If this is less than that, then this will be negative. So we can, since we already know Vx and Vr, we can find this condition a priori. So that's what's going on here, which is interesting. So I find this condition, and I can write these in terms of these guys. So I can write all of this, and I can show that this condition is this condition. Now notice this condition now in terms of parameters. So we can a priori tell you what's going on. It's pi m, rho, delta, so we know all of these numbers. And so we have two tables. We'll solve the problem on this case and this case. And notice now, if I do a little bit of more algebra, I find a condition theta. If theta is less than 0, then we have a solution W star equal to 0. If theta is bigger than 0, then we have the next solution. So let's go to the next solution. And we will talk more about the meaning of all these later. But first, let's do the mathematics. So what are you doing time-wise? Okay, continue. The second case, when it's bigger than 0. In this case, W star x is not 0, but is this. And now we substitute these guys into the two value function equations. And now we solve those value function equations again by using the linear device of the 1983 paper that I wrote, and it works. We did not know when we did the Steckelberg whether it works, but it works, and that was the fortunate part. And so we have another case, alpha. This will be different than those previous ones. And now we have a equation that are more complicated to solve, but there are 4 equations, and we solved them by quartic equation at one time, and here we can solve them as well, and we get a cubic equation in this case. It's because it's not asymmetric. There was a case of asymmetry Nash that was 4-power equation. Now it is 3-power equation. But 3-power equations are also easy to solve. Cubic equations are easy to solve. Mathematica has a solution. MATLAB has a solution. The solution was first done by a mathematician named Cardano. He was an Italian guy. His English name is Cardan, so we can also call it Cardan's solution, unless you are very pure and want to say Cardano's solution. But that's something, and there are a lot of things we have to do in terms of ruling out imaginary solutions and all that, but that is done in the paper. I don't want to get into that. Yeah, so you need Descartes' rule of sign to show that there exists a unique positive real root. Then the 2 remaining roots may be both imaginary and real. And so all of this is done. And you can use Mathematica or a book like a handbook of solution of mathematics handbook. I have this book in my office. It's a used book. It's a handbook. And you can find a solution there. So these are the 3 roots. There's a cubic equation. There's a cubic equation written this way. And a cubic equation this way, if you write 3 solutions where you can see Q and R are given by this. Let me see, there's something missing here. what is missing here is the cubic equation written. And did we write this in a book? Okay, something is missing here, and it actually is now missing here, but it's a slide is not slide. We don't have that. So if you go to the book, you will see this needs to be fixed. This no, it is there. I'm sorry. So it's all clear. So what is going on here is the following. We're defining a quadratic cubic equation by following. We're going to call this A1, this A2, and this A3. So we have an equation called, I think it's better to write the equation one more time. Kushali, can you put this slide and just keep that in mind? I'm going to, after we decide this, that equation becomes beta cube plus A1 beta square plus A2 beta minus A3 equal to 0. That's the whole reason I'm defining this. But it's a good idea.
Or
yeah, on this slide, we're going to squeeze an equation after this. We're going to write an equation called beta cube plus A1 beta square plus A2 beta minus A3 equal to 0. See A1, A2, A3 here? We're going to write, actually it's plus A3 because this is already minus, so it'll be plus A3. Beta cube plus A1 beta square plus A2 beta plus A3 equal to 0, okay?
Okay.
That equation is missing, and it should be written clearly so that we know what's going on. That is our cubic equation.
Is that in the book too?
Now, book also has to be corrected, yes. Okay. Not corrected, it's just a better explanation to have one more equation.
Okay, what slide is this?
Huh?
It's slide 61, right?
Yeah, there's no mistake. We're just going to fix it, okay? Now, once we have that, we can write the three roots in terms of A1, A2, and A3. See, there's a lot of things going on here. A1, A2, A3 are the only parameters now. And Mathematica will tell you that these are the three roots in terms of A1, A2, A3. But then what is S and T? Well, S and T are given like this, where these Q and R in terms of A1, A2, A3. You see how long this procedure is? That solution is A1, A2, A3. But if I were to write S, and then within S I put this will be a long, long expression. All of these three are function of A1, A2, A3, but it's written this way. You write this way, then tell you what S is, then tell you what Q and R are. But it's all mathematical. It's closed form. Everything is completely clear. But it should be, we know the equation we are solving is not written. The equation we are solving is this equation, but I should write this equation as A1, A2, A3. So I will fix it, and I will fix that later, but I'm going to try to see whether I should not write this equation altogether and call that as 13.82. We'll see. Okay. Because I don't want to change equations. Okay. So this is all coming from a course on solving algebraic equations. So we have case q bigger than 0, case 2q less than 0, and we identify. See, this is, even though it is a closed form solution, it's not so easy to solve, or whatever. So if q is bigger than 0, then we have this, and there's only one positive rate and two imaginary roots, and the positive rate is given by this. Case q is less than 0, and this is bigger than 0. There are three real roots, only one positive root, which is this. The third one is this case. S and T are both imaginary. We have three real roots. S and T are imaginary, but the roots are real. While subcases can be given to identify the positive root, for our purpose, it's enough to identify numerically. So there are subcases of which one of the three roots are positive. And that requires, again, a lot of writing, but we just do it here in terms of numbers. So once we have the number, we can tell you what. So what I'm trying to do here is identify which of these root is positive. Notice, you cannot say this is always positive. Sometimes this is positive, sometimes this is positive, sometimes this is positive. Depends on A1, A2, A3. And A1, A2, A3 depends on our parameters. So first we have the parameters, given parameters. From the given parameters, we find A1, A2, A3. Once we find A1, A2, A3, we find beta 1, beta 2, beta 3. And once we find beta 1, beta 2, 3, we identify the real root by these cases. Now, in this case, we go one step lower and we actually give the numbers on pi and this and that, and we will see three roots and we'll take the positive root. But we can prove that only one of them is positive in each of the subcases of case 3. When all is said and done, this is what the paper has. We can identify theta bigger than 0 and theta less than 0 a priori in terms of the parameters of the problem. Once we do that, then in this case, we can solve the value function like this, where alpha and beta are given by this. In this, subsidy rate is 0, and control is given by this. Advertising is given by this. If this is not the case, then this is the case. Where theta is bigger than 0, we have the value function given by these two. And we have beta, beta m, alpha, beta m given by this set of equations, which are not so nicely solvable like this, but they have a solution. And take one of the solution to be the positive solution, which is the beta. Then we can write the subsidy rate given by this. And in this case, when theta is bigger than 0, we know that this quantity is bigger than 0. So this quantity is positive. And then we have the u star x, which is the advertising, given the function of x is this. So this tells you the entire solution. And we will talk more about the interpretation of this solution next week, because there are a lot of tables and I might want to do a little bit more. It might be a good idea for you to read the paper of Hey Prasad and Sethi so that we can, because the paper in the control theory book, I only took these two graphs, okay? But referees would want more description or insight from the solution. We also talk about coordination to some extent. All that is in the paper, so I can bring a few pages of the paper. So I'll talk to Kushali about that later. We will also talk about, so let's plan, let's spend 1 or 2 minutes to plan. I will also talk about, Kushali, please make a note because we will need the book pages or the slides next time, okay? I will also talk about the non-unique solution in control cases, and this is going to be on page 458 of the book. Let me just give you what I'm going to talk about. I'm going to talk about section D.8. It's called the Seti-Skiba points, and I'll talk about that. And Kushali will probably give me ways so that we can display the pages onto the system here. Okay, 458, page 458 to 460, 3 pages. Okay. Other than that, I would like you guys to send me email to see if you want material in the book that you have questions that you might want to say, okay, I want to ask those questions. Then you have to ask me those questions by email, and I can prepare the part of the slides where we will go over that material. So it's kind of a review to some extent. So if you want the course to be reviewed, then tell me what are the issues that you want me to repeat. Okay.